We are going to learn Hermitian operator. What is Hermitian operator? If age is an operator and its adjoint age dagger is equal to age, then the operator is called Hermitian operator. Now this operator has some properties. Properties number 1, that all eigenvalues of age are real. And second is all eigengates are orthogonal. Later we will see that any observable corresponding to any measurement is Hermitian operator. Now we will going to prove these two property. First property, that all eigenvalues are real. Suppose that AI is an eigengate of age and corresponding eigenvalue is lambda I, then age AI equal to lambda I AI. Now the dual correspondence of this relation will be AI age dagger equal to AI lambda star. Now since H is a Hermitian operator, it is self-adjoint. Self means H dagger equal to H. That means this relation can be simplified to AI H equal to AI lambda star. Now if we multiply one from both sides by AI and 2 with AI and then subtract 1 and 2, will get AI age AI equal to lambda I ai ai and ai h ai equal to lambda star ai ai. That means 0 equal to lambda I minus lambda star into ai ai. Now if we assume that ai is not a null gate, then lambda I minus lambda I star should equal to 0. That means lambda I star equal to lambda I. And this means that lambda I is real value. That means all eigenvalues corresponding to H is real value. So we prove the first property. Now we are going to prove the second property, that is all eigengates are orthogonal. To do so, we first write that H ai equal to lambda ai, equation 3, and H aj equal to lambda j aj. Equation 4. We write these two equations as follow from the equation 1 and equation 2 with real eigenvalues lambda. Now if we multiply both sides of equation 3 by aj from left and both sides of equation 4 by ai from right, and then subtract the two equations, we will get aj h ai equal to lambda I aj ai and aj h ai equal to lambda j aj ai. If we subtract these two equations, we will get 0 equal to lambda I minus lambda j into aj ai. Now if we assume that lambda I minus lambda j not equal to 0, then aj ai equal to 0. That means every eigengates of H are orthogonal to each other. So we prove the two following property of Hermitian operator. Now we'll see that any orthonormal eigen k follow the completeness relation. That means any eigen, that means any state can be represented by orthonormal eigen states. Now what what is the condition? Now what is the condition for orthonormal k vectors? That is ai aj equal to delta ij. Now if we multiply ai both sides of the equation, then we'll get ai aj equal to delta ij ai. If we sum the equation over I, then ai aj summation of I delta ij ai, this is nothing but aj. That means summation of I ai acting on aj as an identity operator I. Which means this follows, which means they follow the completeness relation. That means any eigen, any normalized eigen k's can be base case of the Kate space. Now we'll see what measurement does on a state and why any observable to an measurement is a Hermitian operator. So before any measurement, of observable K is made, the state, suppose alpha, can be represented by eigengates of the observable A. Suppose the eigengates are AI, then we can write alpha equal to summation of I AI AI alpha. Now when measurement is performed, the system is thrown into one of the eigenstate of the corresponding observable A. What does it mean? That alpha will thrown into a eigenstate of the measurement observable when a measurement is performed on that state, and the measured quantity will be quantity that will get from the experiment will be the eigenvalue corresponding to the eigengate AI. Now, since in real world any measure quantity is real value, then that means the all eigenvalues of the observable A should be real value, and this property is held by the Hermitian operator. So the observable A should be an Hermitian operator from the two perspective. One is its all eigenvalues should be real value, since in a measurement, in the experiment, the eigenvalues corresponding to the eigenkate we measure from that experiment, and we can also represent any state in terms of eigenkates of an Hermitian operator, since all Hermitian operators are orthogonal to each other. So in that way, from this, since this operator A, that means this observable A should follow the two following property. One is that its eigenkates are orthonormal, and secondly, all eigenvalues are real value. The only operator that follow both of these property is Hermitian. So that is why we use any observable as an Hermitian operator. Now as a real world example. Now in Stern-Gulch experiment, a silver atom with an arbitrary spin orientation will change into either SZ plus half or SZ minus half after going through the experimental setup. That means a AG atom with an arbitrary spin orientation will change its orientation into either in the direction of the magnetic field or in the opposite direction of the magnetic field after it going through the magnetic field. So the measurement, if we want to measure the orientation of the spin of the AG atom, that measurement always change the state of that AG atom in either the direction with the magnetic field or in the opposite direction of the magnetic field. So from this experiment we can see that the measurement actually change the state. So the measurement always change the state after measurement being performed. But the only exception when the measurement does not change the state, only when the state itself are eigenkates of that observable. If the state is an eigenkate of the observable A, then the measurement will not change the eigenkates state of the eigenkates of that state. Now if the observable has more than one more than one eigenkets, then we do not know in advance into which of the various eigenkets the system will thrown into after a measurement being performed. That means if the observable, the operator A has an more than one eigenkets, then we cannot say after the measurement after the measurement being performed into which eigenstate the system is thrown into. So there is a postulate in quantum mechanics that corresponding to the measurement of an observer. Now what is the postulate? Postulate is that the probability for jumping into some eigenkate, suppose A, after the measurement is mod alpha A square, and this is nothing but alpha A into alpha A star. That means alpha A into A alpha or A alpha into alpha A. That is the probability that a system which is in state alpha before the measurement it will go into a eigenstate A after the measurement with probability alpha A square. And what we will get as a measure quantity? That will be the eigenvalue corresponding to eigenkate A. So we will observe or we will measure as a measure quantity the eigenkates corresponding to the eigenvalue corresponding to the eigenkates A. Now if we ask what is the expectation value of the measure quantity, that is nothing but A into lambda A is the sum is our eigencase of the observable A, and lambda is the eigenvalue corresponding to eigencase A. Now this is the probability of measuring lambda as a result of experiment. So what is the expectation of the measured quantity? That will be the probability and the number lambda that is measured in that particular experiment. That means lambda is observed with what probability? Alpha into A mod the square. So what will be the expectation? Expectation will be the summation over A into lambda mod alpha A square. Now this is equal to A alpha A alpha. That means A alpha A since A is the eigencase of observable A, that means A equal to lambda. That means summation of A alpha A equal to alpha A sum over of A alpha. This is the identity, nothing but identity. Since A are the orthonormal eigencases. Why A are the orthonormal eigencases? Because A is the eigencase corresponding to the observable A, and since A is an observable, A is an Hermitian operator, and we know that for an Hermitian operator its eigencases are orthogonal and orthonormal. That means this summation of A bra A kate A into bra A equal to identity operator. That means this is equal to alpha A identity alpha. That means alpha A alpha is the expected measure value.